presentation is an estimation of degree of consolidation for soil improvement projects using preloading. So after introduction, I'm going to introduce a number of methods which can be adopted for the estimation of degree of consolidation. Then after that, I'm going to present 3 to 4 case histories. I believe many of you have been to Singapore. We are a small country, so because of this, we have to do land reclamation to expand the space. So as you can see from here, so in the past a number of years, the total territory has been expanded by more than 10 square kilometers through land reclamation. And well, you can see some of the downtown areas was actually constructed on reclaimed land, including the Marina Bay Sands, which was constructed on a piece of land reclaimed in the recent years. So the pictures showing here are the land reclamation process. So if you come by aeroplane, you have to land at the Changi International Airport, which is also constructed on a piece of reclaimed land. So I was very fortunate to be involved with the Changi East Land Reclamation Project, on which so runway 3 and currently terminal 5 is constructed. So the total area for this land reclamation project is more than 2,000 hectares and used more than 270 million cubic meters of sand and 140 million meters of PVD. So if we use land, if we use sand, and the land reclamation process can be illustrated as follows. So firstly, you place the sand fields on top of the seabed marine clay. So once you form a platform, and then you can start to install PVDs from top of the platform, and then you can use preloading to consolidate the marine clay. So because the marine clay is normally very soft, so we need to improve the marine clay. And one of the most economical way is to do preloading. So preloading either using fuel surcharge or using vacuum preloading. After this, if you have to build the runway on top, you will probably like to densify the sand layer by dynamic or vapor compaction, and before you can construct a runway and use it as an airport. However, in the recent years, there is a shortage of sand fuel materials, so we will have to use seabed marine clay and dredged from the sea as fuel materials, or using waste as fuel materials. So if you are using dredged materials, so there are 2 ways. One is grabbed from the seabed, another one is you use suction dredges and you pumped as a slurry. So in fact, clay fuels were used for a recent land reclamation in Singapore, which is the TWAS land reclamation project. Or land reclamation is also one of the solutions for sea level rise. So as you can see from the picture on top, so perhaps 1/3 of Singapore can be inundated by 2100. So I'm sure many coastal cities, including Bangkok, is suffering from the same problem. And so this is the prediction of the flooding or inundated area in Jakarta. So in Jakarta's solution, or Indonesia's solution, is to build a giant seawall as shown over here. And of course, together with land reclamations. So in addition to the giant seawall, we'll probably have to dredge the many rivers in Jakarta. So the dredged clays that can be used as a fuel for land reclamation. And in fact, using clay slurry for land reclamation is not new. For example, Port of Brisbane is reclaimed using maintenance dredging fuel materials. When soft marine clay is used for land reclamation, and because the ground is relatively soft, we will not be able to use a fuel surcharge anymore. At least we cannot use it entirely using fuel surcharge. So another way is probably using vacuum preloading as shown over here. So you use a suction pump to apply a suction into the marine clay. So then you reduce the pore pressure and to increase the effective stress, so to consolidate the soft clay. And the difference between a fuel surcharge and vacuum consolidation is vacuum create an inward movement, so you will not have stability problem. Of course, today's my task is not to discuss land reclamation method, but to discuss how we estimate the degree of consolidation. And degree of consolidation, and in fact, this is the average degree of consolidation. It's not the degree of consolidation calculated for a point. So the average degree of consolidation is often used as one of the contract specifications. So normally we have to ask the contractor to deliver a piece of land with let's say 90% degree of consolidation. But the problem is the different degree of consolidation values can be obtained depending on the methods adopted in estimating degree of consolidation. So this often leads to dispute between consultant and the contractor. Then what are the methods which we can adopt to calculate degree of consolidation? Our conventional way is to use settlement, and in this way, the degree of consolidation is defined or calculated as a settlement at a given time, let's say 1 year after you start the preloading, over the ultimate consolidation settlement. So this ultimate consolidation settlement can be predicted, let's say using E-log P curve. But the problem is our soil profile can be very complicated. Our design parameters may be too simplified. So in other words, this ultimate consolidation settlement is not easy to predict. So as an alternative, so we sometimes use the field monitoring settlement and to estimate the ultimate degree of consolidation and using a number of methods such as Ahsoka's method. I'm sure many of you in the audience are familiar with this, or the hyperbolic method. Another approach which is not often adopted is to use pore water pressure and monitored. And this is not to use the pore pressure measured at a certain location, but to use the pore pressure distribution over the depths. And in this way, we don't have to estimate the ultimate consolidation settlement. So the degree of consolidation can be purely calculated using the pore pressure monitored in the field. So in other way, the pore pressure, the degree of consolidation estimated using pore water pressure will have no errors involved in humans' judgment, humans' calculation. But if we calculate degree of consolidation using settlement, and so there is a certain degree of human errors involved in the estimation of the ultimate consolidation settlement. Let's briefly introduce the few methods which we normally adopted. And the first one is Ahsoka's method. So for Ahsoka's method, what we have to do is we work out the settlement at a given time, for example, 7 days, 14 days, and 21 days, etc., etc. And then we plot the settlement, let's see, at 7 days versus the settlement at 14 days, etc., etc. So then we have a number of points, and by fitting the points using a straight line, so this straight line is going to intercept with a 45-degree line, and so the intercepting point will be the ultimate consolidation settlement. And using the Ahsoka's method, the slope which we have obtained from this plot, in other words, the beta 1, and we will also be able to calculate or I should say back calculate the coefficient of consolidation, either CH or CV. However, we will have to know at least one of the two values. Either we know CV, we back calculate CH, or the other way around. I just give you an example. So this is the settlement data from one of the soil improvement projects. And so showing over here is the settlement monitored at the different elevations. So the solid dots is at the ground surface. If we use this settlement versus a time curve, we will be able, to divide the settlement for 20 days, 40 days, 60 days, etc., etc. Okay, so we put the numbers over here, and then in this way, and we will be able to plot the settlement at the 20 days and see versus the 40 days. And so at 1 point, and then 40 days versus 6 days, etc., etc. Then we fit those points by a straight line, then we get the ultimate consolidation settlement. However, when we use Ahsoka's method, we have to bear a few uncertainties in mind. And the first one is the ultimate consolidation settlement and can be affected by the time interval I used. So just now I used 20 days, but if you use 10 days, and the ultimate consolidation settlement value may be different. Another problem is, and the curve may be affected by the secondary settlement. And the third is when the degree of consolidation is rather small, let's say less than 70%, then the Ahsoka's method may not be reliable. And this is understandable because just like weather prediction, if you want to predict the weather in a month is not that reliable as compared to predicting tomorrow's weather. The second method is so-called the hyperbolic method, and the original method was developed by two researchers from India. Then subsequently, it was modified by Professor Tan from National University of Singapore. Using this method, you will also be able to work out the ultimate consolidation settlement. And recently, my PhD student, Dr. Gore, has proposed another method. So the difference between this method and the Ahsoka or hyperbolic method is by using Kasi parameter. So as showing over here. So, but of course, to calculate this, you have to know nu, you have to know mu. Mu is the standard Hansberg's factor, and then this nu is calculated by CH using CV and times the thickness of the compressible clay layer and over the diameter of the equivalent drain, and this nu is from the Hansberg's equation. So using this, you will be able to fit your settlement in the same way, but the only difference is instead of using settlement at I plus 1 versus settlement at I, and you use a power of 1 over this see. So from here, you will be able to get the curve fitting, and from here you get the ultimate consolidation settlement. And one of the advantages of using this method is and this curve fitting and tend to be more reliable. And secondly, you will be able to back calculate your CV, CH, by knowing the ratio between CV and the CH. So normally it is easier to estimate the ratio by CH and CV. So for example, for recent deposits or upper marine clay in Singapore, so this is normally somewhere between 2 to 3. So this is easier to estimate rather than by guessing what is a CV or CH value. I will not be able to explain the details of this method, but however, I can refer you to 3 of the recent publications, and basically, and here I give you the details for the so-called modified Ahsoka method and modified hyperbolic method. So that's using settlement. And if we are using pore pressure, so what we have to do is, we can plot the pore pressure and distribution and versus depth. So the pore pressure distribution should be within the 2 lines. The first line is the hydrostatic pore pressure line, and the second line is the initial pore water pressure line. So if you put a surcharge, for example, 100 kPa as your delta sigma V, and your excess pore pressure will increase by 100 kPa. So if it's for land reclamation, so the load is applied over a larger extent, then the 100 kPa increase in pore pressure and should be everywhere. Okay, increase by 100 kPa. If you have a single drainage, let's say you wait for half year, and then the pore pressure will dissipate from the initial pore pressure line and to the line over here. So from here, you will be able to calculate the areas between the hydrostatic pore pressure line and the initial excess pore pressure line. So this as your denominator, and then you calculate the area within the existing pore pressure distribution and the hydrostatic line as your numerator. And from here, you will be able to calculate the average degree of consolidation. So just to give you an example, so this is for preloading case, and if you know the pore pressure distribution at the 4 points showing over here, and you will be able to calculate the areas between the so-called initial pore pressure line, the hydrostatic line, and the areas covered by the current pore pressure, covered by the 4 yellow triangle and the hydrostatic line. So the ratio between the 2 areas will give you the average degree of consolidation. So this is for fuel surcharge, but you may be wondering, what if I use vacuum preloading? Okay, the calculation will be more or less the same. So let's assume this is your hydrostatic line. Assuming you may have some initial excessive pore pressure, so your pore pressure may not be exactly at the hydrostatic. So after you have applied vacuum, let's say 80 kPa, so then this will be a suction line. The suction line is formed by, translate, horizontally your hydrostatic line by the amount of suction, let's say 80 kPa to the left, so there will be a suction line. So again, you can calculate the areas between the initial pore pressure distribution and the suction line as your denominator, and then you calculate the areas covered by the current pore water pressure and the suction line. So as the numerator, so from here, you work out your average degree of consolidation. So just give you an example, so this is one of the vacuum preloading projects which we analyzed almost 12 years ago. almost 20 years. So as you can see from here, so this is the initial pore pressure distribution. The dashed line is the hydrostatic. So then another dashed line is the suction line, which is moved inward parallelly by 80 kPa. So the curves in between are pore pressure at 30 days, 60 days, 90 days, etc., etc. So just using the areas which I have mentioned, so you can calculate, okay, the degree of consolidation for 30 days, 60 days, 90 days, etc., etc., or at the end of the project. So we also compare the degree of consolidation from the settlement. So basically, you can see if you have a degree of consolidation of 80 and above, the comparison is quite reasonable. From here, you can see the degree of consolidation from settlement is larger than the degree of consolidation from pore water pressure, even for at the end, although the two are rather close, and this is for a very good reason. The reason for this is because when we put our pore pressure transducers, we want to measure where the pore pressure is the greatest. For example, we put pore pressure, in between the PVDs and where the pore pressure tend to be the largest. But however, when we measure settlement, and we want to measure at a point where the settlement may be the largest, for example, the center of the embankment load. So as a result, we actually overestimate the settlement, so which will tend to overestimate the degree of consolidation. But on the other hand, if you overestimate your pore pressure, you will tend to underestimate your degree of consolidation. So as a result, so the degree of consolidation from settlement in theory should be bigger or slightly bigger than the degree of consolidation from pore water pressure. But nevertheless, when the degree of consolidation is more than 85%, and the difference tend to be small. So now let's move on to case history. So I'm going to introduce the first case, which is a storage yard using combined vacuum and fuel surcharge. And the case was presented in one of the papers by Prof.Jian and myself in Canadian Geotechnical Journal in 2005. So this is the area where vacuum preloading was applied. So of course, settlement as well as piezometers, settlement gauges as well as piezometers were installed to measure settlements at the different elevations as well as pore pressures at the different elevations. So here are the soil profiles. And I have to say this is a reclaimed land. So even the top layer you see is clay slurry, okay, and muddy clay, etc., etc. Only after this you have your seabed marine clay. And so over in general, so all the soil layers are clay, and the initial water content you can see are higher than the liquid limit, which is in red. And void ratio is also very big. The preloading started with a vacuum of 80 kPa until 40 to 50 days. And before the fuel surcharge was applied in stages until a fuel surcharge of 40 kPa. So this is a combined vacuum plus fuel surcharge case. So this is the ground settlement monitored. And you can see, okay, more than 1.6 meters of settlement has developed under the fuel surcharge. So this is the settlement measured at different durations, at different elevations. So this is the pore pressure measured at different elevations in the soil. So now let's concentrate on the pore pressure. So if we plot the pore pressure measured in this graph versus the depths, and then we can have the pore pressure or the initial pore pressure. As I said, this is a reclaimed land, so the initial pore pressure is higher than the hydrostatic, which is showing over here. So if you apply a vacuum for 30 days, and this is a pure vacuum, and the fuel surcharge has not been applied, and so you can see the reduction from the initial pore pressure up to the pore pressure over here. Of course, if you go to 60 days, so the pore pressure will go to the solid red points. But remember, in between, we have to apply the 40 kPa excess pore water pressure. So once the fuel surcharge is applied and the excess pore pressure will be generated, so the excess pore pressure will have to be on the right-hand side of 40 kPa from the initial pore pressure. So that would be the pore pressure with excess pore pressure with the pore pressure generated by the surcharge. And so if you wait for the final of the consolidation, so the pore pressure will come to here. So similarly, I'm calculating the area by the highest pore pressure boundary and the suction line, which is over here, and over the area by the final pore pressure distribution over the suction line, you will be able to calculate the degree of consolidation by pore pressure of 82 kPa. But if you use a settlement, so you get 82%. And then if you use a settlement, you get 87%. So again, the degree of consolidation from settlement is greater than the degree of consolidation from settlement, and this is because of the instrumentation. Now move on case history 2, which is Changi's land reclamation project. And so this the detail of this project is also presented in a paper in 2009. So basically the case is for pilot test with PVDs of different spacing. So for example, 1.7 in square, 1.5 meters in square, and 2 meters in square, with a compare where there's no rain. Okay, so here are the soil profiles, and although we try to choose a more or less uniform soil profile, but nevertheless you can still see within a short distance of 230 to 280 meters, and the soil profile is very erratic with the sand lengths embedded in between. Nevertheless, so this is a settlement monitored at different elevations for green spacing of 1.5 meter. So this is the pore pressure monitored for a green spacing of 1.5 meters. Well, I'm not going to discuss how we estimate the degree of consolidation using settlement, because most of you are familiar with this. So I'm going to illustrate how the degree of consolidation is estimated using the pore water pressure as shown over here. So similarly, we can plot the pore pressure distribution versus depths. So for a lot 1.5, and that refers to from the lot where the PVD is 1.5 meters. So if we plot the points, and then the other points in red. We also plotted the pore pressure for compare in hours without the PVD lot X. So those are the pore pressures, in yellow. Okay, so you can see the difference with the PVD. Of course, the pore pressure is dissipated further. So with the surcharge, so the excess pore pressure line is over here. Okay, so this should be the initial, the highest pore pressure. Then with time, the pore pressure is going to dissipate. Without drain, and there's not much pore pressure dissipation. With a drain of a spacing of 1.5, the pore pressure is dissipated over here. But interestingly, if based on the settlement monitoring data, for the compare where there is no PVD, we still get a degree of consolidation of 77%, which of course will not be reliable. Okay, how do we know it's not reliable? Well, we can use the pore pressure and estimate the degree of consolidation. So if we use the yellow points, and we will get the degree of consolidation of 38%, and rather than 77%. But however, if we use the pore pressure distribution in red, okay, this is for a PVD of 1.5 meters, and we can get 85% and degree of consolidation. So this 85 and compares rather well with the degree of consolidation for the degree of consolidation for lot 1.5, okay, which is 91%. Yeah. By the way, we actually verified the pore pressure for the compare for lot X, because one of the arguments is whether the pore pressure measurements are indeed reliable. So what we did is we put the CPT. So we put the CPT in somewhere close to the piezometers for lot X, and we do a PVD, we do a CPT holding test and to measure the pore pressure, and then we compare with the piezometers, and indeed, so those points are relatively consistent. So in other words, the CPT is given in okay, the CPT actually given in the yellow. The piezometer is given in the triangle. You can see the triangle and the yellow dots are rather consistent. So in other words, so the pore pressure distribution is verified. The case 3 is for land reclamation of slurry pond showing over here. And this is also part of the Changi East land reclamation project. And in this pond, the clay slurries was deposited over the past years, as you can see from here, and the water content of the slurries is very high, ranging from 100 to 300%, and that's basically no shear strength. You can see from here, very, very small, even up to 20 meters. So you can see from here, okay, the green side distribution curve. So all the particles are within the clay range. So for land reclamation, so what we have to do is we have to use a floating pontoon to spread sand layer by layer on top of the soft mud. Then after that, we install PVDs from the top of platform. Just indicate how soft is the clay. You can see the mud shoot out around the mandrel when PVDs were installed. So here are the instrumentation scheme. So here are the settlement monitored versus the time. So from the surface settlement, we can estimate the degree of consolidation to be 91. And from the piezometers, okay, we will be able to estimate the degree of consolidation to be 42%, and by plotting the pore pressure versus the depth, and by using the method which I have explained. So, and over here we have another inconsistency. You see here, if we use a settlement, we get 91, and if we use a pore pressure, we get 42. So which one is correct? And the one using 91 is incorrect. And the reason is because if it's in slurry form, in fact, you have a settlement, but the settlement is actually caused by the sedimentation. So in other words, your clay particles are not in contact. So you do not have effective stress development, you do not have pore pressure dissipation, although you have settlement. So if we are using slurry for land reclamation, so probably we will have to use pore pressure to estimate degree of consolidation rather than using settlement, because the settlement can be misleading. So this is one of the examples. And to verify this 42% is indeed more representative, and we also plotted the Andrew shear strength profile from vein shear as well as from CPT. So basically, you can use the same method as for pore pressure. So if you use the initial vein shear profile, you can assume let's say for 90% degree of consolidation, your Andrew shear strength is going to increase by how much. You can calculate this using a simple calculation. So this will be the Andrew shear strength when 90% degree of consolidation has been achieved. So this is the current Andrew shear strength profile, and using the areas in between in the same way as for pore pressure, we will be able to estimate, okay, the overall degree of consolidation to be somewhere of 45%. By knowing the vertical degree of consolidation is 10%, we can calculate the degree of consolidation due to horizontal or radial drainage is 40%. So this agree very well with this 42% and pore pressure estimation. But some of the further data and the further experience were actually summarized in some of the publications showing over here. And also in one of the book chapters in the ground improvement book and Creech and Bear. The last case was actually from engineer Anthony Wong, and he's doing a master currently at NTU, and he is an engineer in Hong Kong with Hong Kong Engineering Development Office. So this case history is for a trial embankment in Hong Kong. So one set is deep cement mixing, another set is by PVD, you can see. And the case history which I'm going to share and from Anthony's analysis is more for the PVD, not for the deep cement mixing. So this is the land reclamation picture showing the land reclamation. So here are the instrumentation profile. I just want to show you the soil profile. Okay, so top you have the fuel materials, and then follows by the marine clay, and ranging from -6 to -20. So here are the instrumentations. So the more important data is the ground settlement curve, as well as the pore pressure distributions, at the different time intervals, let's say 150 days and 210 days and 270 days, etc., and the corresponding to different pore pressure and profiles. So illustrating the pore pressure is indeed dissipating over the time, okay, and together with settlement development. And using the settlement data and the Ahsoka's plot, hyperbolic plot, as well as Gore's plot was constructed over here. And from here, we will be able to estimate the ultimate consolidation settlement. And if you use Ahsoka, you get 2.48. If you use Gore's method, you get 2.47. If you use hyperbolic, you get 2.34. So there are some differences, but in general, the differences are not that significant. But if we use pore water pressure, we will be able to estimate the degree of consolidation and by pore water pressure by the open triangle. So the open triangle is by pore pressure data. From here, you can see the pore pressure data actually agrees well and with the Ahsoka's degree of consolidation prediction as well as the Wall's method. The hyperbolic tend to overestimate the degree of consolidation for this particular case. So in summary, the average degree of consolidation can be estimated using both settlement and pore pressure data monitored in the field. Estimating degree of consolidation using settlements, the ultimate consolidation settlement has to be predicted using either Ahsoka or hyperbolic method. A new method by Pore and Chu is also introduced, which allows the CV or CH value to be back calculated. The pore water pressure distribution can also be used to estimate the degree of consolidation using a method suggested by Chu and Yan in 2005. A suggested procedure is for us to estimate degree of consolidation using settlement, but however, we should use degree of consolidation by pore pressure as a verification. And sometimes if the difference between the two is too big, as in the slurry pond land reclamation case, and then we have to ask ourselves, what's the reason for the large discrepancy? From there, we will be able to use our engineering judgment to find out the errors involved in the degree of consolidation estimation. Yeah, so with this, I finished my presentation, and thank you very much. And take this opportunity, I would also like to thank my PhD students, master students, as well as my researchers, and also thank my funding agencies for the general support.